Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Perhaps you've had a long day, or maybe you're someone who prefers drifting off to sleep while contemplating the vast, slow-moving forces that have shaped our planet rather than counting sheep. Either way, tonight's journey is for you. You have nothing to do but rest. Let your mind settle, your breathing slow, and your body grow comfortable as gravity itself seems to soften around you. Tonight, we're traveling to some of the coldest, most remote places on Earth. We're exploring glaciers, those massive rivers of ice that flow across continents and down mountainsides, moving so slowly that their journey is measured not in days or months, but in years, decades, and centuries. These frozen giants hold most of Earth's fresh water. They carve valleys, grind mountains, and reshape entire landscapes with patient, relentless force. They are archives of ancient air, witnesses to climate shifts spanning hundreds of thousands of years, and harbingers of changes yet to come. We'll drift gently from their formation in high mountain cirques to their role in the great ice ages that periodically transformed the planet. We'll explore how they move, how they sculpt the land beneath them, and how they're responding to our warming world. Some of what you hear tonight may surprise you, or at the very least spark some quiet curiosity as you drift toward sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a peaceful way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin our journey into the world of ice. The birth of ice, how glaciers form. A glacier begins not with ice, but with snow. Simple, delicate snowflakes falling from winter clouds, accumulating layer upon layer, year after year. In most places, this snow melts away each spring, returning to liquid water that feeds streams and rivers. But in certain special locations, where the air remains cold enough throughout the year, the snow persists. It survives the summer, and when the next winter arrives, new snow falls on top of the old, and the process begins again. These places exist primarily in two types of locations. The first are high altitudes, where mountain peaks pierce into the frigid upper atmosphere. Even near the equator, mountains tall enough will have permanent snow on their summits. The second type of location is at high latitudes, near the poles, where the sun's rays arrive at such an angle that they never deliver quite enough warmth to melt all the winter's accumulation. In these frozen realms, at the roof of the world or the ends of the earth, glaciers are born. The transformation from snow to ice is a slow metamorphosis that unfolds over years and decades. Fresh snow is remarkably fluffy, filled with air pockets between its delicate crystalline structures. When you scoop up fresh snow, you're holding something that's perhaps 90% air and only 10% frozen water. It's light, soft, and easily compressed. But as new snow continues to accumulate above, the weight begins to compress the layers below. The pointed arms of the snowflakes break off. The spaces between crystals shrink. Air pockets are squeezed smaller and smaller. After a year or two of this compression, the snow transforms into something called firn, though some call it neve. This is an intermediate stage between snow and ice. Firn has a granular texture, denser than snow, but not yet the solid blue ice of a glacier. It looks almost like coarse salt or sugar, and if you were to hold it in your hand, you would notice it's much heavier than an equal volume of snow. The transformation continues. More snow falls. More weight presses down. The firn compacts further, and its ice crystals begin to bond together more tightly. The remaining air pockets become smaller and more isolated, trapped as tiny bubbles within the growing mass of ice. These air bubbles are precious to scientists because they contain samples of the atmosphere from the year the snow originally fell, creating a chronological archive of Earth's air composition stretching back hundreds of thousands of years. Eventually, after decades or even centuries depending on the rate of snowfall and the local climate, the compacted firn becomes true glacial ice. At this point, it has transformed into a solid crystalline mass, bluish in color because it absorbs other wavelengths of light while reflecting blue back to our eyes. This ice is remarkably dense, with air content reduced to perhaps 20% or less. And crucially, it has reached a thickness and mass sufficient to begin moving. This is what defines a glacier. It's not simply a large mass of ice. It must be ice that flows. Most scientists agree that for accumulated ice and snow to be called a glacier, it needs to be at least about 100 meters thick at some point, though smaller permanent ice masses are sometimes included in glacier inventories. Once the ice reaches roughly 30 to 40 meters in depth, something remarkable happens. The sheer weight of the ice above creates enough pressure on the ice below that it begins to deform. The solid ice, which seems so rigid and unyielding, actually begins to behave almost like a very thick, viscous fluid on geological timescales. This deformation is the beginning of glacial flow. Under immense pressure, ice crystals can slowly slide past one another, or entire layers can creep downward and outward. If the glacier sits on a slope, gravity pulls it downhill. If it covers a vast area like the ice sheets of Antarctica or Greenland, it flows outward in all directions from the thickest central dome, like honey spreading slowly across a table, except taking thousands of years to move distances that honey would cover in seconds. But the formation of a glacier requires more than just cold and snow. It requires a specific balance. The amount of snow that falls and accumulates during the cold season must exceed the amount that melts, evaporates, or sublimates during the warm season. This balance is called the glacier's mass budget. In the accumulation zone, typically at higher elevations or in the coldest regions, snow and ice are added faster than they're removed. In the ablation zone, usually at lower elevations or margins, ice melts or breaks off faster than it's replenished. Between these zones lies the equilibrium line, where gain and loss balance out. The position of this line determines whether a glacier is growing or shrinking. If the equilibrium line moves higher up the glacier, the ablation zone expands and the glacier retreats. If it moves lower, the accumulation zone expands and the glacier advances. This dynamic equilibrium means that glaciers are constantly responding to climate conditions, advancing during cooler periods and retreating during warmer ones, though their response is slow and delayed, sometimes by decades. The conditions that allow glacier formation exist across a wide range of environments. In polar regions like Antarctica and Greenland, temperatures remain below freezing year-round, but snowfall can be surprisingly low. Parts of Antarctica receive less precipitation than the Sahara Desert. Yet, glaciers thrive there because the little snow that does fall never melts. In contrast, some coastal mountains in temperate latitudes receive enormous amounts of snowfall, enough to build substantial glaciers, even though summer temperatures rise well above freezing. The coastal ranges of Alaska and southern Chile host impressive glaciers for this reason. Wind plays an important but often overlooked role in glacier formation. Strong winds can transport snow from exposed areas and deposit it in sheltered basins, concentrating the accumulation in specific locations. Some glaciers form almost entirely from wind-drifted snow. These are sometimes called drift snow glaciers, and they can exist in places where direct snowfall alone would be insufficient to sustain them. The time required for a glacier to form varies tremendously. In areas with heavy snowfall and cold temperatures, a glacier might develop over a few centuries. In drier, colder regions, the same process could take millennia. Some of Earth's glaciers have been growing and flowing continuously for tens of thousands of years, while others are relative newcomers, having formed during the last few thousand years during particularly cold periods. One fascinating aspect of glacier formation is that it creates a feedback loop. As snow and ice accumulate and begin to reflect more sunlight back into space, the local area becomes cooler, which allows even more snow and ice to persist. Snow and ice have a high albedo, meaning they're highly reflective. Fresh snow can reflect up to 90% of incoming sunlight, while darker surfaces like soil or vegetation might absorb 80 to 90%. This reflectivity is one reason why glaciers, once started, can grow relatively quickly under the right climate conditions. But forming a glacier requires patience. It cannot happen overnight or even over a few winters. It requires the steady, persistent accumulation of snow, year after year, the gradual compression under its own weight, and the slow transformation of ephemeral snowflakes into solid, flowing ice. It is geology in slow motion, climate made visible, time compressed into layers of frozen water that hold stories of seasons and centuries. A gallery of giants, types of glaciers. Glaciers come in a remarkable variety of forms, each shaped by the landscape it occupies and the climate that sustains it. While they all share the fundamental characteristics of being masses of ice that flow under their own weight, the differences between a small mountain glacier clinging to a steep slope and the vast ice sheet covering Antarctica are striking. Understanding the different types of glaciers helps us appreciate the diversity of frozen landscapes across our planet. The broadest division separates glaciers into two main categories: alpine glaciers and continental glaciers. Alpine glaciers, also called mountain glaciers or valley glaciers, are constrained by the topography around them. They form in mountainous regions and flow downhill through valleys carved by rivers or by previous generations of glaciers. Continental glaciers, often called ice sheets when they're very large, are so massive that they cover the underlying landscape entirely. flowing outward in all directions from their thickest points. Let's begin with alpine glaciers, since they're more numerous and accessible. The most iconic type is the Valley Glacier, a river of ice flowing down a mountain valley. These glaciers typically originate in bowl-shaped depressions near mountain peaks called cirques. Snow accumulates in these natural amphitheaters, compacts into ice, and eventually overflows the cirque's rim, beginning its descent down the mountainside. As the glacier flows down valley, it's constrained by the valley walls on either side, giving it a distinctive tongue or ribbon-like shape when viewed from above. Valley glaciers can be quite long. Some extend for dozens of miles from their high-altitude sources to their termini at lower elevations. The Hubbard Glacier in Alaska stretches for over 70 miles from its accumulation zone to where it meets the sea. As valley glaciers descend, they often merge with tributary glaciers flowing from side valleys, much like rivers and their tributaries, growing larger and more powerful as they gather more ice. Another type of alpine glacier is the Cirque Glacier, smaller and simpler than valley glaciers. These occupy only the bowl-shaped cirques high on mountainsides and don't extend far beyond. They're wide but short, contained within their mountain hollows. Many cirque glaciers are the remnants of once larger valley glaciers that have retreated upward during warmer periods, surviving only in the highest, coldest locations. When valley glaciers emerge from mountain ranges onto flatter terrain, they can spread out laterally, forming what's called a Piedmont glacier. No longer confined by valley walls, the ice spreads like a fan or lobe across the adjacent plains. The Malaspina Glacier in Alaska is a spectacular example, covering over 1,500 square miles as it spreads across coastal lowlands. From above, Piedmont glaciers can look almost like frozen puddles spreading at the base of mountains. Hanging glaciers are another dramatic alpine type. These cling to steep mountainsides, sustained by ice falling from higher elevations, or by snow accumulating directly on the steep slopes. They don't have well-defined accumulation or ablation zones, and are often unstable, with chunks of ice regularly breaking off in avalanches that thunder down the mountainside. Ice aprons are thin sheets of ice plastered against steep mountain faces, while ice caps are larger features that cover the tops of mountains or high plateaus, flowing outward in multiple directions. Ice caps are similar to ice sheets but much smaller. The definition often used is that ice caps cover less than 50,000 square kilometers, while ice sheets are larger. Iceland hosts several significant ice caps, including Vatnajökull, the largest in Europe by volume, covering an area the size of Cyprus. Now, we turn to the true giants, continental glaciers or ice sheets. Only 2 proper ice sheets exist on Earth today. The Antarctic ice sheet is by far the largest, covering an area of about 14 million square kilometers, roughly the size of the United States and Mexico combined. It contains approximately 6.5 million cubic kilometers of ice, which represents about 90% of all the ice on Earth and nearly 70% of all the fresh water. If the Antarctic ice sheet melted completely, global sea level would rise by approximately 58 meters, or about 190 feet. The Greenland ice sheet is the second largest, covering about 1.7 million square kilometers, roughly 80% of Greenland's land area. It contains enough ice to raise sea level by about 7 meters if it melted entirely. Both of these ice sheets are so thick that their essential regions sit atop ice that is 3 to 4 kilometers deep. The pressure at the base is so immense that the ice there can be near its melting point despite the frigid surface temperatures. Ice sheets don't respect underlying topography the way alpine glaciers do. They bury mountains, fill valleys, and create their own geography. The surface of an ice sheet is shaped primarily by the pattern of snow accumulation and the flow of ice, not by the bedrock hidden far beneath. Only the tallest peaks protrude through the ice as nunataks, lonely islands of rock in a frozen ocean. Where ice sheets meet the ocean, they often extend out over the water as ice shelves. Vast, floating platforms of ice still attached to the land-based ice sheet. The Ross ice shelf in Antarctica is larger than France. These ice shelves don't directly raise sea level when they melt because they're already floating, displacing their weight in water. But they act as buttresses, holding back the faster flow of grounded ice behind them. When ice shelves collapse, the glaciers feeding them can accelerate, contributing more ice to the ocean. Outlet glaciers are the fast-moving streams of ice that drain ice sheets and ice caps. They're essentially valley glaciers that originate within a larger ice mass, channeling ice through gaps in coastal mountains or areas of lower elevation. Jakobshavn Isbrae in Greenland is one of the most studied outlet glaciers in the world, and one of the fastest moving, capable of flowing up to 40 meters per day during peak flow periods. Tidewater glaciers are another important category, defined by the fact that they terminate in the ocean. These can be either alpine glaciers descending from mountains to the sea, or outlet glaciers draining ice sheets. Where they meet the water, large chunks of ice regularly break off in a process called calving, creating icebergs. The calving face of a large tidewater glacier is one of nature's most spectacular sights. A towering cliff of blue and white ice that periodically collapses into the sea with thunderous roars and enormous splashes. Rock glaciers represent an interesting hybrid. These are masses of rock debris with interstitial ice or an ice core, flowing slowly down slopes. They are found in cold mountain regions and look more like slow-moving rivers of rock than traditional glaciers, but they flow through similar mechanisms. Each type of glacier represents an adaptation of ice to its environment, a different expression of how frozen water responds to climate, topography, and gravity. From the smallest Cirque glacier to the continent-spanning ice sheets, they all share fundamental behaviors, while displaying remarkable diversity in form and character. They are the planet's frozen rivers, its reserves of solid water, flowing and reshaping the world at a pace that makes years pass like seconds. Rivers of ice. How glaciers move. One of the most fascinating aspects of glaciers is that they move. Ice, which seems rigid and immobile, actually flows. Not quickly, not obviously if you're watching, but with a patient, inexorable motion that carries rock, sediment, and sometimes even forests downhill or outward across landscapes. Understanding how glaciers move requires us to recognize that ice, under the right conditions of pressure and temperature, behaves very differently from how we experience it in our everyday lives. Glaciers move through two primary mechanisms: internal deformation and basal sliding. Both processes typically operate simultaneously, though their relative importance varies depending on the glacier's temperature, thickness, and the steepness of the underlying terrain. Internal deformation is perhaps the more surprising of the two mechanisms. Under the immense pressure created by the weight of overlying ice, individual ice crystals can slowly deform and reorient themselves. This process is called creep, though it's nothing like the creep of a vine growing up a wall. This is solid ice moving like a very viscous fluid on timescales of years. The ice crystals don't melt. Instead, they undergo plastic deformation, slowly flowing past one another in response to stress. This deformation isn't uniform throughout the glacier. The greatest movement occurs in the deepest ice, where pressure is highest. Near the surface, the ice is relatively rigid and brittle, forming what glaciologists call the fracture zone, typically the upper 30 to 50 meters. This brittle surface ice is carried along by the flowing ice beneath it, like a rigid raft floating on a slow-moving current. When this brittle surface ice encounters changes in the slope or width of the glacier bed, it can crack, forming crevasses. The rate of internal deformation depends strongly on temperature. Ice at temperatures near its melting point deforms much more easily than very cold ice. This is why polar glaciers, where temperatures can be 20 or 30 degrees Celsius below freezing, move much more slowly than temperate glaciers, where ice temperature hovers near 0 degrees Celsius. Temperature affects the bonds between ice crystals, making them easier or harder to break and reform. The second mechanism of glacier movement is basal sliding. This occurs when a thin layer of liquid water exists at the base of the glacier, allowing the entire mass of ice to slide over the bedrock or sediment beneath it like a sled on a film of water. This water can form through several processes. The pressure of the overlying ice can depress the melting point of ice at the base, causing it to melt even though the temperature is below 0 degrees Celsius at normal pressure. This is the same principle that allows ice skaters to glide as the pressure under the blade melts a thin film of water. Meltwater from the surface can also work its way down through cracks and crevasses to the glacier bed, providing lubrication. During summer, when surface melting is most active, the amount of water reaching the glacier base increases, and many glaciers speed up. This seasonal acceleration has been well documented on glaciers around the world. Some glaciers can double or triple their speed during the melt season. The nature of the bed itself matters enormously. If the glacier rests on hard, smooth bedrock, basal sliding may account for only a small fraction of the glacier's motion. But if the base sits on soft, water-saturated sediment, the glacier can plow through or slide over this deformable bed, potentially accounting for most of its movement. Some glaciers in Iceland and parts of Antarctica move primarily by deforming the sediment beneath them, rather than by deforming the ice itself. Friction plays a complex role in glacier movement. At the base and sides of a glacier, friction with bedrock or sediment resists motion. causing the ice to move more slowly there than in the center or near the surface. In valley glaciers, this creates a velocity profile where the fastest ice is in the middle of the glacier, both laterally and at mid-depth. The slowest ice is at the bottom and sides, dragging against the valley floor and walls. This differential motion creates internal stresses within the ice. The speed of glaciers varies enormously. Many glaciers creep along at rates of just a few centimeters per day, moving perhaps 10 to 30 meters in a year. At this pace, it would take ice a century to travel 3 kilometers. Other glaciers move much faster. Some outlet glaciers in Greenland and Antarctica can move tens of meters per day, traveling several kilometers in a year. The fastest glacier ever reliably measured is Jakobshavn Isbra in Greenland, which during periods of peak flow has been clocked at speeds exceeding 40 meters per day. Some glaciers exhibit surges, sudden increases in speed that can see them advance several kilometers in just a few months or years. Glacier surges are dramatic events where ice that has been slowly accumulating in the upper reaches of a glacier suddenly releases, rushing down valley at speeds many times faster than normal. A glacier that typically moves 10 meters per year might, during a surge, move 100 meters per day. After the surge, the glacier returns to its normal slow pace, having transferred a large volume of ice to lower elevations. The mechanisms behind surges are still not fully understood, but they're thought to relate to changes in basal water pressure and the thermal regime at the glacier bed. Some glaciers surge regularly, with intervals of several decades between events, suggesting an internal cyclical process. Others surge unpredictably. The variegated glacier in Alaska is one of the most studied surge-type glaciers, having been intensively monitored during its 1982-1983 surge. Obstacles on the glacier bed affect flow in complex ways. Where ice flows over a bump or step in the bedrock, it speeds up on the upstream side and slows on the downstream side, creating stresses that can open crevasses. In regions where the glacier bed has an uneven or undulating surface, the glacier surface can develop wave-like features called ogives, arcuate bands that appear below ice falls. These curved patterns, often marked by alternating dark and light bands, form because ice that passes through an icefall in summer experiences more melting than ice that passes through in winter, creating annual layers visible from above. Icefall regions, where glaciers flow over particularly steep terrain, are spectacularly chaotic. The ice stretches and fractures extensively, creating a jumbled maze of crevasses, ice blocks called seracs, and unstable towers. The Khumbu Icefall on Mount Everest is perhaps the most famous example, a dangerous section that mountaineers must navigate on their way to the summit. Ice moves through icefalls faster than in other parts of the glacier because of the steep slope, but the surface becomes so broken that it's difficult to recognize it as a coherent glacier at all. In some locations, glaciers can move so slowly that they're essentially stagnant. Trees have been observed growing on the surfaces of some Alaskan glaciers where movement has ceased and enough sediment has accumulated to provide soil. These dead ice regions are still technically part of the glacier, but no longer participate in active flow. The movement of glaciers is fundamentally driven by gravity, but the details involve a complex interplay of pressure, temperature, water, and the physical properties of ice itself. It's a process that unfolds on timescales that challenge human perception. If you stood beside a glacier for an hour, or even a day, you'd likely see no movement at all. But return year after year, and you'd witness the slow but inexorable downstream progress of the ice, carrying with it everything embedded within and resting upon it. Glaciers may be rivers of ice, but they're rivers that measure their journeys in decades and centuries, rather than minutes and hours. The anatomy of a glacier. To understand a glacier fully, we need to look at its structure, to see it not as a simple block of ice, but as a complex, layered system with distinct zones, internal features, and dynamic processes at work from its surface down to its bed. A glacier has an anatomy as surely as a living organism does, though its organs and tissues are made of ice, rock, and water. At the largest scale, glaciers divide into two primary zones based on their mass balance. The accumulation zone is the upper region where snow and ice are added faster than they're removed. This is typically the highest, coldest part of the glacier. Here, snow falls and compacts, becoming firn and eventually ice. The surface of the accumulation zone might be covered in fresh snow for much of the year, and the net effect over time is that the glacier surface rises as more mass is added. The ablation zone is the lower region where ice and snow are removed faster than they're added. Here, melting is the dominant process, though sublimation, where ice transitions directly to water vapor without becoming liquid, and calving, where chunks of ice break off, also remove mass. In the ablation zone, the glacier surface is often bare ice rather than snow, especially by late summer. Over time, the surface here lowers as more ice is lost than gained. Between these zones lies the equilibrium line, sometimes called the snow line. This marks the elevation where accumulation and ablation balance over the course of a year. Above this line, the glacier gains mass. Below it, the glacier loses mass. The position of the equilibrium line fluctuates from year to year depending on weather and climate, but its average position over several years determines whether the glacier is in balance, advancing, or retreating. If we could slice through a glacier and look at its internal structure, we'd see layers like those in sedimentary rock, each representing a year's snowfall. These annual layers are often visible as slight differences in density, grain size, or trapped impurities. In the accumulation zone, they're relatively distinct. But as ice flows deeper and experiences more pressure and deformation, the layers become distorted and folded, eventually becoming unrecognizable in the oldest, deepest ice. Ice cores drilled from glaciers and ice sheets preserve these annual layers for hundreds of thousands of years. Scientists can count the layers back in time like tree rings, determining the age of ice at different depths. But the real treasure in ice cores comes from the tiny air bubbles trapped in the ice. These bubbles are samples of the ancient atmosphere, allowing scientists to measure past concentrations of carbon dioxide, methane, and other gases. Ice cores from Antarctica provide climate records extending back over 100,000 years, an extraordinary archive of Earth's climate history. The surface of a glacier is rarely smooth. Crevasses are perhaps the most obvious features, deep cracks that can extend 30 to 50 meters down into the ice, occasionally even deeper. These form in the brittle, rigid ice of the fracture zone when the ice is stretched or sheared. Transverse crevasses run perpendicular to the glacier's flow and form where the glacier accelerates, such as when it flows down a steeper slope. The ice extends, and cracks open perpendicular to the direction of stretching. Longitudinal crevasses run parallel to flow and form where a glacier spreads laterally, such as when emerging from a narrow valley onto a wider plain. The ice extends sideways, opening cracks parallel to the flow. Marginal crevasses form near the edges of glaciers, where friction with valley walls creates shear stresses. These crevasses often angle across the glacier, forming a herringbone pattern. Where crevasses intersect, isolated pinnacles and blocks of ice called seracs can form. Seracs are unstable and can collapse without warning, making crevassed areas extremely dangerous to traverse. The beautiful blue color often visible in crevasse walls comes from the same optical effect that makes the sky blue. Ice absorbs red wavelengths of light and scatters blue wavelengths, and the effect is pronounced in the dense, bubble-free ice exposed in crevasse walls. Moulins are vertical shafts in glaciers, cylindrical wells that can extend from the surface down to the bed. They form when surface meltwater exploits existing cracks or weak zones and drills its way down through the ice. The water spirals down these shafts, sometimes with considerable force during warm summer days when surface melting is rapid. Moulins connect the glacier surface to its base, providing pathways for meltwater that can lubricate the bed and affect glacier flow. Medial moraines are distinctive dark stripes running down the center of many valley glaciers. These form when two glaciers merge, and their lateral moraines, the debris accumulating along their edges, combine into a single stripe down the middle of the merged glacier. On some large valley glaciers with multiple tributaries, there can be dozens of parallel medial moraines, creating a striking striped appearance from above. At the glacier's base lies a realm rarely seen but critically important to understanding glacier behavior. The bed can be smooth bedrock, rough and fractured rock, or soft sediment. Subglacial water, flowing in channels or spread in thin sheets, can exist even beneath glaciers whose surfaces are well below freezing. This water affects friction, lubrication, and the glacier's ability to erode its bed. Some glaciers have been found to sit atop large subglacial lakes, pools of water trapped beneath the ice by the insulating effect of the ice itself and the heat from the Earth's interior. The thermal structure of a glacier significantly affects its behavior. Temperate glaciers have ice at or near the melting point throughout their depth. These are typically found in maritime climates with relatively warm winters and abundant snowfall. Cold glaciers have ice well below freezing throughout. These are common in polar regions and high-altitude environments. Polythermal glaciers have a mix, with cold ice in some areas and temperate ice in others. The thermal structure affects how the glacier moves, how much water is present at its base, and how effectively it erodes the underlying rock. Some glaciers develop internal drainage systems, networks of tunnels and channels within or at the base of the ice that carry meltwater. These in-glacial and subglacial channels can be tens of kilometers long. The outflow from these drainage systems is often a milky, turbulent stream emerging from the glacier's terminus, colored by suspended rock flour, the fine sediment ground from bedrock by the glacier's erosive power. In the ablation zone, especially on some lower elevation glaciers, supraglacial features can include streams, ponds, and even small lakes forming on the glacier's surface during warm weather. These can persist for weeks or months, slowly moving downstream with the ice. Some eventually drain through moulins, while others may evaporate or freeze when temperatures drop. Dirt and rock embedded in the ice, especially near the base and sides, give glaciers their erosive power. This debris acts like sandpaper, grinding away at the bedrock as the glacier moves. The concentration of rock and sediment is often highest at the base where the glacier scrapes along the ground, and at the sides where material falls onto the glacier from valley walls. A glacier, then, is not a simple, uniform mass. It's a dynamic, structured body with zones of accumulation and ablation. Layers recording time, crevasses recording stress, internal channels carrying water, and debris-laden ice, grinding away at the rock beneath. It's a complex system, shaped by temperature, snowfall, gravity, and the landscape it occupies. To know a glacier is to understand that beneath its seemingly static surface lies motion, memory, and the power to reshape the solid earth itself. Sculptors of stone, glacial erosion, and landforms. Glaciers are among the most powerful agents of erosion on Earth. Over thousands and millions of years, they have carved some of the world's most dramatic landscapes, from the fjords of Norway and New Zealand to the valleys of Yosemite and the lakes of the Canadian Shield. The erosive power of glaciers comes from their immense weight, their ability to transport enormous volumes of rock and sediment, and the relentless grinding action as they move across the land. Glaciers erode through two primary mechanisms: abrasion and plucking. Abrasion is exactly what it sounds like. As a glacier moves, the rock fragments and boulders embedded in its base act like the teeth of a giant rasp, scraping and grinding against the bedrock beneath. This process is most effective when the ice is sliding over its bed, and when there's a good supply of rock particles embedded in the basal ice. The result is a smoothing and polishing of the bedrock surface, creating what geologists call glacially polished rock. The fine sediment produced by this grinding is called rock flour. Particles so small they range from 0.00 to 0.0625 millimeters in diameter. Rock flour gives glacial meltwater streams their characteristic milky turquoise color. The suspended particles scatter light in specific ways, creating those stunning colors that make glacial lakes and rivers so visually striking. When you see a brilliant turquoise lake at the foot of a glacier, you're looking at billions of tiny rock particles suspended in the water. Abrasion also creates glacial striations, long parallel scratches carved into bedrock. These striations are remarkably useful to geologists because they record the direction of ice movement. By mapping striations across a landscape, scientists can reconstruct the flow patterns of glaciers that disappeared thousands of years ago, In places that were covered by ice sheets during the last glacial period, you can still find bedrock outcrops with crisp, clear striations pointing the direction the ice once flowed. Plucking, sometimes called quarrying, is a different process. It occurs when a glacier breaks off and removes chunks of bedrock rather than simply grinding them smooth. This happens most effectively on the downstream side of bedrock bumps, where the ice pulls away from the rock. Water seeps into cracks in the bedrock. When it freezes, it expands, wedging the rock apart. The glacier then plucks these loosened blocks from the bed and carries them away embedded in the ice. Plucking is more effective in fractured or jointed rock, where natural weaknesses provide places for water to penetrate. Together, abrasion and plucking sculpt distinctive landforms. One of the most recognizable is the U-shaped valley. Rivers carve V-shaped valleys with steep sides and a narrow bottom. But when a glacier occupies a river valley, it widens and deepens it, plucking and abrading the sides and floor. The result is a valley with a broad, flat or gently rounded floor and steep, nearly vertical walls. A distinctive U-shape visible in cross-section. Yosemite Valley in California is perhaps the most famous example. Its nearly vertical granite walls rising thousands of feet above the flat valley floor. Hanging valleys are another characteristic feature. These are smaller tributary valleys that enter a main glacial valley high up on the valley wall rather than at the level of the valley floor. They form because the larger glacier in the main valley carved down more deeply than the smaller glaciers in the side valleys. When the glaciers melted, the tributary valleys were left hanging high above the main valley, often with spectacular waterfalls dropping from their mouths. Yosemite Falls plunges from a hanging valley, dropping 740 meters in 3 distinct sections. At the heads of valleys, glaciers carve bowl-shaped depressions called cirques. These amphitheater-like basins form through a combination of plucking, abrasion, and freeze-thaw weathering on the steep back wall. When a glacier melts and retreats, it often leaves a cirque lake or tarn cradled in the rock basin. When multiple cirques form on different sides of a mountain and erode backward into the peak, they can create sharp ridges called arêtes and pointed pyramid peaks called horns. The Matterhorn in the Alps is the archetypal horn, its distinctive shape carved by glaciers eroding from all sides. Fjords are among the most dramatic glacial landforms. These are deep, narrow inlets of the sea, often extending tens or even hundreds of kilometers inland, with steep walls rising hundreds of meters on either side. Fjords form when glaciers carve valleys that extend below sea level, deepening them to great depths. When the glaciers retreat and sea level rises, the ocean floods these over-deepened valleys, creating fjords. Norway's coastline is famous for its fjords, as are parts of Chile, New Zealand, Alaska, and British Columbia. As glaciers transport rock and sediment, they deposit it in characteristic patterns. Moraines are accumulations of this glacial debris. Lateral moraines form along the sides of valley glaciers, accumulating from rockfall from the valley walls and from material the glacier scrapes from its sides. Terminal or end moraines form at the furthest extent of a glacier's advance, marking where the glacier deposited debris as it melted. These can form ridges and hills that remain in the landscape long after the glacier has retreated. Recessional moraines mark positions where a retreating glacier paused temporarily during its overall retreat. Ground moraine is a more diffuse deposit, a veneer of glacial debris spread across the landscape as the glacier melts. This creates gently rolling topography rather than distinct ridges. Much of the northern United States and Canada is covered with ground moraine deposited by ice sheets during the last glacial period. Drumlins are streamlined, elongated hills composed of glacial till, shaped like inverted spoons lying on their sides. They form beneath moving ice, sculpted by the flowing glacier. Drumlins typically occur in fields of hundreds or thousands, all aligned with the direction of ice flow. The blunt end faces upstream, and the tapered end points downstream. The Finger Lakes region of New York and parts of Ireland have spectacular drumlin fields. Eskers are long, sinuous ridges of sand and gravel, sometimes extending for dozens of kilometers. They form in subglacial or end-glacial meltwater channels. As the glacier melts, these tunnel deposits are left behind as ridges standing above the surrounding terrain. They're valuable to geologists as indicators of subglacial drainage patterns and to society as sources of sand and gravel. Erratics are boulders transported by glaciers and deposited far from their source. Some erratics are enormous, house-sized rocks sitting incongruously on landscapes entirely different from the bedrock they rest upon. These boulders can be traced back to their sources, sometimes hundreds of kilometers away, providing evidence of glacial flow paths. The term glacial erratic comes from their wandering nature, rocks that have erred far from home. Glaciers also create features through deposition in water. Glacial lakes form in depressions carved by ice or dammed by moraines. In these lakes, sediment settles in annual layers called varves. Each year, coarser sediment washes in during spring and summer melting, followed by finer sediment settling out in the calmer winter water. These paired light and dark layers can be counted like tree rings, providing precise dating for geological events. The Great Lakes of North America are the most spectacular legacy of glacial erosion. They occupy basins carved and deepened by repeated advances of ice sheets over millions of years. The weight of the ice depressed the crust, and glacial scouring excavated river valleys. When the ice retreated roughly 10,000 years ago, these basins filled with meltwater, creating the largest group of freshwater lakes on Earth by total area, holding about 21% of the world's surface fresh water. Glacial erosion operates on vast scales and over immense timescales. The Scottish Highlands, the Alps, the Rocky Mountains, the Himalayas, and countless other mountain ranges bear the unmistakable signature of glacial sculpting. The smooth, polished bedrock, the U-shaped valleys, the hanging valleys with their waterfalls, the cirques and arrêts, the fjords cutting deep into coastlines, all are the work of ice, patiently carving and shaping stone over tens of thousands of years. In this way, glaciers are not merely repositories of water or indicators of climate. They are active sculptors, artists working in stone and ice, creating landscapes of profound beauty and drama. The power they wield comes not from speed, but from persistence. The unrelenting pressure of immense weight moving slowly but surely across the face of the earth grain by grain and boulder by boulder, reshaping mountains and carving valleys that will endure long after the ice itself has melted away. The Great Ice Ages. Our planet has not always looked as it does today. At multiple times in Earth's history, vast ice sheets have spread across continents that are now temperate or tropical, burying entire landscapes under kilometers of ice. These periods, known as ice ages or glacial periods, have profoundly shaped the world we inhabit. Understanding them helps us comprehend not just the past, but also the present and future of our climate. The term Ice Age can be confusing because it's used in two different ways. Strictly speaking, an ice age is a long period of Earth's history characterized by the presence of permanent ice sheets on at least one continent. By this definition, we are currently in an ice age, one that began approximately 2.6 million years ago, when ice sheets developed on Antarctica and Greenland, and have persisted ever since. This ice age, called the Quaternary glaciation, is still ongoing. Within ice ages, the climate oscillates between colder periods when ice sheets expand, called glacial periods or glacials, and warmer intervals when ice sheets retreat, called interglacial periods or interglacials. We are currently in an interglacial period called the Holocene, which began approximately 11,700 years ago, when the massive ice sheets that covered much of North America and Europe melted back to their present extent. The last glacial period, often called the last glacial maximum, when referring to its coldest point around 20,000 years ago, saw ice sheets covering Canada and the northern United States, most of Britain and Scandinavia, and extending south into Germany and Poland in Europe. The Laurentide ice sheet over North America was up to 3 kilometers thick in places. So much water was locked up in ice that global sea level was approximately 120 meters lower than today, exposing vast areas of continental shelf. The English Channel was dry land. You could walk from Siberia to Alaska across the Bering Land Bridge. Australia and New Guinea were connected. The climate during glacial periods was not uniformly colder everywhere. While regions near the ice sheets were bitterly cold, some areas experienced different effects. Many regions that are now deserts received more rainfall during glacial periods. The Sahara, for instance, was much wetter. Trade wind patterns shifted, and the polar front, the boundary between cold polar air and warmer temperate air, moved equatorward, affecting climate patterns globally. The cause of these glacial interglacial cycles is complex, but a key factor is variations in Earth's orbit and axial tilt, collectively known as Milankovitch cycles after the Serbian scientist Milutin Milankovic, who developed the theory. Earth's orbit around the Sun is not perfectly circular. It's slightly elliptical, and the degree of ellipticity changes over about 100,000 years. The tilt of Earth's axis also varies between about 22.1 and 24.5 degrees over roughly 41,000 years. Additionally, the axis itself wobbles like a spinning top, completing a precession cycle every 26,000 years. these orbital variations change the amount and distribution of sunlight reaching Earth's surface at different latitudes and seasons. They don't change the total amount of sunlight Earth receives by much, but they affect when and where it arrives. High, northern latitudes during summer are critical because glaciers can survive if summers are cool enough that not all the previous winter's snow melts. When the Milankovitch cycles combine to produce cooler northern summers, snow accumulates year after year, glaciers grow, and ice ages intensify. However, orbital forcing alone isn't enough to explain the magnitude of glacial interglacial climate change. Feedback mechanisms amplify the initial changes. Ice and snow have high albedo, reflecting more sunlight back to space than darker surfaces like ocean or vegetation. As ice sheets grow, they increase Earth's overall reflectivity, cooling the planet further, which allows ice sheets to grow even more. This is a positive feedback loop. Another crucial feedback involves carbon dioxide and other greenhouse gases. Ice core records show that atmospheric CO2 concentrations during glacial periods were around 180 to 200 parts per million, while during interglacials they rose to about 280 parts per million. Lower CO2 levels during glacials contributed to cooler temperatures. The exact mechanisms that caused CO2 to decline during glacials are still debated, but likely involve changes in ocean circulation and biological productivity. The Quaternary Ice Age has been characterized by repeated cycles, with major glacials occurring roughly every 100,000 years over the past million years. These cycles are visible in ocean sediment cores, ice cores, and other geological records as oscillations in temperature, ice volume, and atmospheric composition. At least 17 major glacial-interglacial cycles have occurred during the Quaternary. But the Quaternary is not Earth's only ice age. The planet has experienced multiple ice ages throughout its 4.6 billion year history. Evidence exists for ice ages around 24 to 21 billion years ago, around 720 to 635 million years ago, the Cryogenian period, when Earth may have been a snowball Earth with ice covering even the tropics, and several others. Ice ages are relatively rare events in Earth's history. For most of its existence, Earth has been warmer than today, with little or no permanent ice. Within the broader Quaternary Ice Age, recent millennia have shown interesting variations between approximately 10,000 and 5,000 years ago. During the early to middle Holocene, many regions were warmer than present, a period sometimes called the Holocene climate optimum. Glaciers retreated to extents smaller than today in many mountain ranges. More recently, a period called the Little Ice Age affected much of the world from roughly 1300 to 1850, with the coldest period around 1600 to 1800. This was not a true ice age, but rather a period of relative cooling within the current interglacial. Mountain glaciers advanced significantly during this time. Alpine glaciers descended further into valleys, destroying farms and villages. The Thames River in London froze regularly, allowing frost fairs to be held on the ice. The causes of the Little Ice Age are debated, but likely included reduced solar activity, increased volcanic eruptions, which inject sunlight-reflecting particles into the atmosphere, and changes in ocean circulation. Since the mid-1800s, Earth has warmed, and glaciers worldwide have retreated. This warming initially reflected natural recovery from the Little Ice Age, but has been greatly amplified by human-caused increases in greenhouse gas concentrations. The rate of warming and glacier retreat since the mid-20th century is unprecedented in the geological record of the Holocene. Understanding ice ages is crucial for understanding our current climate. The interglacial periods of the past 800,000 years typically lasted 10,000 to 20,000 years before conditions gradually cooled into the next glacial. The current interglacial, the Holocene, is about 11,700 years old. Without human influence, Earth might naturally be heading slowly toward the next glacial over the coming tens of thousands of years. However, human activities have altered atmospheric composition so significantly that we've likely delayed or even prevented the next glacial period. Ice ages remind us that Earth's climate is not static. It has changed dramatically in the past and will change in the future. The ice sheets that once covered much of the northern continents are gone, but Greenland and Antarctica still preserve ice from glacial times. Beneath their surfaces lie ice layers up to hundreds of thousands of years old, holding bubbles of ancient air and clues to past climates. In studying ice ages, we study not just the past, but glimpse the mechanisms that drive climate change. Mechanisms that operate over timescales, from years to hundreds of thousands of years, driven by forces both terrestrial and astronomical. Modern retreat, glaciers, and climate change. The glaciers of the world are melting. This statement, stark and direct, is one of the most visible and undeniable manifestations of our warming climate. From the Alps to the Andes, from Alaska to the Himalayas, glaciers are retreating at rates unprecedented in the historical record. Understanding what's happening to glaciers, why it's happening, and what it means for the future is crucial, because glaciers are not just beautiful natural features. They're critical components of Earth's climate system and essential resources for human civilization. When we speak of glaciers retreating, it's important to understand what this means. Glaciers don't move backward like a car in reverse. Instead, their terminus, the downstream end of the glacier, moves up valley because ice is melting or breaking off faster than new ice is arriving from upstream. The ice itself continues flowing downhill, but the melting at the terminus outpaces the supply, causing the glacier's edge to recede up valley, exposing bare rock or sediment that was recently buried beneath ice. This process has been documented photographically for over a century. Repeat photography, where pictures are taken from the same vantage point decades apart, provides striking visual evidence of retreat. The Muir Glacier in Alaska, photographed in 1882 and again in 2005, shows transformation so dramatic it's hard to believe it's the same location. In 1882, the glacier filled the entire valley, a massive river of ice flowing to the camera's foreground. By 2005, the glacier had retreated over 50 kilometers up the valley, replaced by open water and exposed rock. What was once solid ice is now a fjord. Similar documentation exists for glaciers worldwide. In the Alps, historic photographs from the 1800s show glaciers descending into valleys where now there are forests, meadows, or bare moraines. In the Himalayas, glaciers that once extended kilometers beyond their current positions have retreated, leaving behind debris-covered slopes and glacial lakes. In South America, Patagonian glaciers that filled valleys with ice now terminate high in mountain cirques, having lost vast volumes. The evidence of glacier retreat is overwhelming. Since 1850, the end of the Little Ice Age, glaciers worldwide have lost substantial mass, but the rate of loss has accelerated dramatically. The World Glacier Monitoring Service tracks hundreds of glaciers globally and has found that 2023 was the third consecutive year in which its reference glaciers lost more mass than they gained. Over the period from the 1970s to the early 2020s, these reference glaciers lost the equivalent of more than 20 meters of water, as if a 90-foot slab had been sliced off the top of each glacier. Scientists measure glacier changes through multiple methods, each providing different insights. The most direct method involves physically visiting glaciers and measuring their mass balance, the difference between accumulation and ablation over a year. Researchers insert stakes into the ice at various elevations, then return annually to measure how much the glacier surface has risen or fallen around each stake. In the accumulation zone, the surface typically rises as new snow and ice are added. In the ablation zone, the surface lowers as ice melts away. By combining measurements from multiple stakes across the glacier, scientists calculate the overall mass change. These measurements are labor-intensive, requiring expeditions to remote, often dangerous locations, sometimes multiple times per year. As a result, only a few hundred of the world's 200,000-plus glaciers have long-term mass balance measurements. But the glaciers that are measured serve as reference glaciers, providing detailed records that help scientists understand how glaciers respond to climate variations. Satellite technology has revolutionized glacier monitoring. Satellites can observe virtually all glaciers, even in the most remote regions. Different satellite instruments measure different aspects of glaciers. Optical satellites capture visible images, allowing measurement of glacier area and the position of terminus. Radar satellites can penetrate clouds and operate in darkness, providing year-round monitoring, and through interferometric techniques, measurements of ice surface elevation changes and flow velocities. Laser altimetry, particularly from NASA's ICESat and ICESat-2 missions, precisely measures ice surface elevation. By comparing measurements from different years, scientists calculate how much ice thickness has changed, which translates directly to mass change. Gravimetric satellites like GRACE and GRACE-FO measure tiny changes in Earth's gravitational field caused by mass changes, including the loss of ice from glaciers and ice sheets. These satellites can detect mass changes integrated over large regions, providing independent confirmation of other measurement methods. Recent studies using satellite imagery have mapped over 200,000 glaciers worldwide, achieving over 97% coverage of Earth's glaciated areas. These studies show that glacier mass loss accelerated from about 0.8 meters of water equivalent per year in the 90s to approximately 1.3 meters per year by the 2010s. Between 2000 and 2019, glaciers lost roughly 257 gigatons of ice per year on average. To put that in perspective, 1 gigaton is 1 billion metric tons. This loss is contributing significantly to global sea level rise. Not all regions are losing ice at the same rate. Some of the fastest losses are occurring in the European Alps, where some projections suggest that glaciers could lose 70 to 80% of their volume by 2100 under current warming trends. The glaciers of the Caucasus Mountains, Central Europe, New Zealand, and tropical regions are experiencing even more dramatic retreats. At current rates, many smaller glaciers in these regions will disappear entirely within the next few decades. Alaska's glaciers are losing mass rapidly, contributing more to sea level rise than the entire Greenland ice sheet during some periods. The Muir Glacier in Alaska has retreated more than 8 kilometers since the late 1800s, transforming a landscape once filled with ice into open water and exposed rock. Patagonia's glaciers are thinning and retreating rapidly. The Uppsala Glacier in Argentina has lost about half its area since the early 20th century. The Himalayan glaciers, often called the water towers of Asia, are thinning and retreating at alarming rates. These glaciers feed major rivers including the Ganges, Indus, Brahmaputra, and Yangtze, providing water to roughly 2 billion people. Studies suggest that Himalayan glaciers have lost about 40% of their area since the Little Ice Age. If current trends continue, some projections indicate that many Himalayan glaciers could lose 2/3 of their volume by 2100, with severe implications for water supplies in one of the world's most populous regions. The causes of this widespread glacier retreat are understood. The primary driver is rising global temperatures caused by increased atmospheric concentrations of greenhouse gases, particularly carbon dioxide and methane. Since the Industrial Revolution, human activities, primarily the burning of fossil fuels and deforestation, have increased atmospheric CO2 from about 280 parts per million to over 420 parts per million as of 2023. This represents an increase of more than 90% in a geological blink of an eye. Greenhouse gases trap heat in the atmosphere, causing global temperatures to rise. The average global temperature has increased by about 1.1 degrees Celsius since the late 1800s, with most of this warming occurring since 1980. This seemingly small increase has had dramatic effects because glaciers are sensitive to temperature changes. Even a small increase in average temperature means more days above freezing, longer melting seasons, and less snow accumulation in winter. For glaciers, the balance between accumulation and ablation is critical. In recent decades, accumulation has not changed dramatically in most regions, but ablation has increased substantially. Warmer summers mean more melting. Warmer winters mean that more precipitation falls as rain rather than snow, even at high elevations that historically received only snow. The equilibrium line, where accumulation equals ablation, has moved upward in elevation on most glaciers. This expands the ablation zone and shrinks the accumulation zone, driving overall mass loss. The consequences of glacier retreat are numerous and severe. The most globally significant is the contribution to sea level rise. Glaciers and ice caps, excluding the Greenland and Antarctic ice sheets, have contributed roughly 1% of observed sea level rise over the past 2 decades. While this is smaller than the contributions from thermal expansion of seawater and ice sheet loss, it's still substantial. Since 1900, global sea level has risen by about 20 centimeters, and glaciers have accounted for a significant fraction of this rise. Sea level rise has serious consequences for coastal communities worldwide. Higher sea levels increase the frequency and severity of coastal flooding during storms. They cause erosion of beaches and coastal habitats. They increase saltwater intrusion into freshwater aquifers, threatening drinking water supplies. Low-lying island, nations, and densely populated coastal areas in developing countries face existential threats from even modest sea level rise. Beyond sea level rise, glacier retreat threatens water supplies. In many regions, glaciers act as natural reservoirs, storing water as ice during cold, wet seasons, and releasing it as meltwater during warm, dry seasons when water demand is highest. This is particularly important in regions with distinct wet and dry seasons. In the Andes, for example, cities like Lima, Peru, depend heavily on glacial meltwater during the dry season. As glaciers shrink, the seasonal timing and quantity of water flow changes, often with an initial period of increased flow as the ice melts, followed by dramatic decreases once the glaciers have largely disappeared. In the Himalayas, hundreds of millions of people depend on rivers fed by glacial meltwater for drinking water, irrigation, and hydropower. A study suggested that by the late 21st century, glacier melt contribution to rivers like the Ganges could decline by up to 2/3, creating severe water shortages in regions where water stress is already a concern. Glacier retreat also creates natural hazards. As glaciers melt, they often form lakes dammed by glacial moraines or ice itself. These glacial lakes can grow rapidly and are sometimes unstable. If a moraine dam fails, or if ice holding back the lake collapses, the result can be a glacial lake outburst flood, a sudden release of enormous volumes of water that can travel dozens of kilometers downstream, destroying everything in its path. These events have killed thousands of people in the Himalayas, Andes, and other mountain regions. Ecosystems are also affected. Many cold-water fish species depend on glacial streams. As glaciers shrink, these streams warm, and their flow patterns change, often making them unsuitable habitat. Plant and animal communities adapted to glacial environments face habitat loss. In the long term, entire ecosystems structured around the presence of glaciers may be fundamentally altered or lost. Recent dramatic events highlight how rapidly some glaciers are changing. In November and December 2022, the Hectoria Glacier in Antarctica retreated by about 8 kilometers in just 2 months, one of the fastest retreats ever recorded. This glacier, roughly the size of Philadelphia, sits on the Antarctic Peninsula, one of the fastest warming regions on Earth. Researchers studying the event found that the rapid retreat occurred because the glacier's base was at sea level on a gently sloping bed, a configuration that makes glaciers vulnerable to rapid collapse once retreat begins. This discovery raised concerns because if larger Antarctic glaciers with similar configurations begin retreating at comparable rates, it could dramatically accelerate sea level rise. Antarctica contains enough ice to raise global sea level by about 8 meters, if it all melted, though such complete melting would take many centuries under any realistic scenario. Even partial melting could be catastrophic. The West Antarctic ice sheet alone contains enough ice to raise sea level by 3 to 4 meters, and parts of it are considered vulnerable to relatively rapid collapse. Greenland's ice sheet is also losing mass at an accelerating rate. Between the early 2000s and the late 2010s, Greenland's rate of ice loss quadrupled. A significant portion of this loss comes from outlet glaciers accelerating and delivering more ice to the ocean, where it melts or breaks off as icebergs. Warm ocean water reaching the bases of these glaciers through fjords has been found to cause extensive melting from below, a process called undercutting that can destabilize glaciers even if air temperatures don't change dramatically. Despite the overwhelming trend of glacier retreat, a few glaciers in certain regions have been advancing or remaining stable. Some glaciers in the Karakoram range of the western Himalayas have grown slightly in recent decades, an anomaly sometimes called the Karakoram anomaly. This appears related to regional climate patterns that have brought increased snowfall to that particular area, enough to offset warming. However, this is an exception, not the rule, and even these glaciers may begin retreating if warming continues. The future of the world's glaciers depends primarily on how much additional warming occurs, which depends on human actions regarding greenhouse gas emissions. If emissions are drastically reduced and warming is limited to 1.5 degrees Celsius above pre-industrial levels, many glaciers will continue retreating, but some could stabilize. If emissions continue at current rates and warming reaches 3 to 4 degrees Celsius or more by 2100, the consequences are stark. Under high emission scenarios, studies suggest that many small glaciers could disappear entirely, and even large glaciers and ice sheets could experience dramatic losses. The glaciers of the world are sending us a clear message. They're sensitive indicators of climate change, and they're responding to the warming we've caused. Their retreat is not just an aesthetic loss or a problem for future generations. It's happening now, with real consequences for water supplies, sea level, ecosystems, and communities around the world. In the ice, we can read both the past and a warning about the future. Water towers of the world. Glaciers are often called the water towers of the world, and this description is apt. They store vast quantities of fresh water in solid form, holding it through cold seasons and releasing it as meltwater during warm, dry periods when water is most needed. For hundreds of millions of people living in or downstream from glaciated mountain regions, glaciers are not merely distant natural wonders, but essential components of their water supply systems, affecting everything from drinking water to agriculture to hydroelectric power generation. To understand the importance of glaciers as water resources, we need to recognize the scale of fresh water they represent. Glaciers and ice caps, excluding the Antarctic and Greenland ice sheets, contain enough water to raise global sea level by about half a meter, representing hundreds of thousands of cubic kilometers of ice. The Greenland and Antarctic ice sheets together hold over 68% of Earth's total fresh water. While most of this ice is not directly accessible as a water resource, its very existence influences global ocean levels, currents, and climate patterns. But it's the mountain glaciers and smaller ice caps that play the most direct role in human water supplies. These glaciers feed major river systems on every continent except Australia. In South America, glaciers in the Andes feed rivers that provide water to tens of millions of people. Cities including Lima, La Paz, and Quito depend significantly on glacial meltwater, particularly during dry seasons when rainfall is scarce, but water demand for drinking and agriculture is high. Lima, Peru, is a particularly striking example. With a population of over 10 million people, it's one of the world's largest cities located in a desert. Annual rainfall is minimal, often less than 20 millimeters per year. The city depends on rivers descending from the Andes, rivers fed substantially by glacial melt during the dry season. As Peruvian glaciers retreat, studies suggest that dry season water availability could decline substantially in the coming decades, creating serious challenges for a rapidly growing population. In Asia, the importance of glaciers is even more pronounced. The Hindu Kush-Himalaya region, sometimes called the Third Pole because it contains more ice than anywhere except Antarctica and Greenland, feeds 10 of Asia's largest rivers, including the Indus, Ganges, Brahmaputra, Mekong, Yangtze, and Yellow rivers. These rivers provide water to roughly 2 billion people, roughly 1/4 of the global population. Agriculture, industries, and ecosystems across India, Pakistan, Bangladesh, China, Nepal, Bhutan, Myanmar, Thailand, Vietnam, Cambodia, and Laos all depend on water from these river systems. The Indus River, flowing through Pakistan and India, is heavily dependent on glacial meltwater and snowmelt from the Himalayas and Karakoram ranges. The river supports one of the world's most extensive irrigation systems, the Indus Basin Irrigation System, which waters agricultural lands feeding over 300 million people. Studies suggest that glacial melt contributes 40 to 50% of the Indus's annual flow, with even higher contributions during summer months. The Indus Basin is already water-stressed, with demand often exceeding supply. Further reductions in glacial water could create serious agricultural and water supply challenges. The Ganges River, sacred in Hinduism and the lifeline for hundreds of millions in India and Bangladesh, receives water from numerous Himalayan glaciers. While monsoon rains provide the majority of annual flow, glacial melt is critically important during pre-monsoon periods from March to June, when agricultural water demand is high, but rainfall hasn't yet begun. The Gangotri Glacier, one of the largest sources of the Ganges, has been retreating rapidly, having lost over 850 meters of length since 1780, with retreat accelerating in recent decades. As this and other source glaciers shrink, the timing and reliability of Ganges flow during critical agricultural periods may change significantly. The Brahmaputra, one of the world's largest rivers by discharge, also originates in glaciated regions of the Himalayas and Tibet. Its flow is crucial for Bangladesh, where the river, combined with the Ganges, creates one of the world's most extensive delta systems. Changes in glacial contribution to the Brahmaputra could affect not just water supply, but also sediment delivery to the delta, which is important for maintaining land in a region where millions live just above sea level and are already vulnerable to sea level rise and tropical storms. In Central Asia, rivers flowing from the Tian Shan and Pamir mountain ranges provide water to Kazakhstan, Kyrgyzstan, Tajikistan, Turkmenistan, and Uzbekistan. These are arid regions where river water is absolutely essential for agriculture and domestic use. The Aral Sea disaster, where the sea shrank to a fraction of its former size due to diversion of its source rivers for irrigation, demonstrates the region's water stress. Glaciers in these mountains are retreating, and projections suggest that water availability in Central Asian rivers could decline significantly by mid-century, potentially exacerbating political tensions over water rights among the downstream nations. The role of glaciers in these river systems varies by season and location. In some rivers, particularly in drier regions like the Indus Basin, glacial melt provides a substantial fraction of annual flow, sometimes 30 to 40% or more during summer months. In other systems, like the Ganges, monsoon rains dominate annual flow, but glacial melt remains critically important during pre-monsoon periods when water demand is high, but rainfall hasn't yet arrived. The pattern typically works like this. During winter, snow accumulates in the mountains, including on glaciers. In spring, snow begins to melt at lower elevations, swelling rivers. As summer progresses, the snow line retreats upward, and glacial ice begins melting, maintaining river flows through hot, dry months. This natural timing, with maximum flow arriving during the hottest, driest period, is enormously beneficial for agriculture and water supply. It's a hydrological system that human societies have adapted to over centuries. But as glaciers shrink, this system is changing. In the short term, increased melting can actually boost summer flows as glaciers lose mass more rapidly. Some regions have experienced increased water availability over recent decades as their glaciers have melted more intensively. But this is temporary. Eventually, as glaciers shrink to a fraction of their former size or disappear entirely, the water they once stored and released will be gone. Annual river flows may decrease, but more significantly, the seasonal timing of flows will change, with more water arriving early in the season from rainfall and snowmelt, and less arriving during the hottest months when it's most needed. This change poses serious challenges for water management. Reservoirs and dams can partly compensate by storing water from wet periods for use during dry periods. But building adequate storage capacity is expensive, politically complex, and environmentally challenging. In many regions, particularly in developing countries, the infrastructure and resources for adapting to changed water availability are limited. Hydroelectric power generation is another critical glacier-dependent resource in some regions. In the Alps, Scandinavia, and parts of the Pacific Northwest of North America, rivers fed by glacial melt support hydroelectric dams that generate significant fractions of regional electricity. In Norway, hydropower provides over 90% of electricity, with glacial melt contributing to the rivers that power the turbines. As glaciers shrink, the reliability and output of these hydroelectric systems may decline, forcing greater reliance on alternative energy sources. Agriculture is perhaps the most glacier-dependent sector in many regions. Irrigated agriculture in Central Asia, parts of South Asia, and Western South America relies heavily on river systems fed by glacial melt. In some areas, as much as 80 to 90% of irrigation water comes from glacial sources during critical growing periods. Crops including wheat, rice, cotton, fruits, and vegetables depend on this water. As glaciers shrink and river flows become less reliable, agricultural productivity could decline significantly, affecting food security for millions of people. The ecological role of glacial meltwater is also important. Cold, clear, glacial streams provide specialized habitats for fish and invertebrates adapted to these conditions. Many salmon species spawn in glacially fed streams, and their populations are closely tied to glacial conditions. As glaciers retreat and streams warm, these species face habitat loss. In the long term, entire aquatic ecosystems could be transformed, with cold-adapted species declining or disappearing, and warmer water species expanding their ranges. Beyond direct water supply, glaciers influence regional microclimates. The presence of large masses of ice affects local temperature, humidity, and precipitation patterns. Glaciers create katabatic winds, cold air draining downslope from ice surfaces. They moderate summer temperatures in nearby valleys. As glaciers disappear, these local climatic effects diminish, potentially affecting agriculture, ecosystems, and human comfort in mountain regions. In some areas, glaciers are already so diminished that their role as water sources has declined dramatically. Bolivia's Chacaltaya Glacier, once the world's highest ski area, disappeared entirely by 2009. Venezuela lost its last glacier in 2004. These disappearances have more symbolic than practical impact because these were small glaciers, but they represent the future for many larger glaciers if current trends continue. The global picture is one of glaciers providing crucial buffering for water supplies, smoothing out seasonal variations, and providing reliable flows during dry periods. But this buffering capacity is declining as glaciers shrink. In some regions, the decline is already measurable and problematic. In others, it will become apparent in the coming decades. The challenges are greatest in regions where populations are large, economic resources are limited, and dependence on glacial water is high. Conditions that unfortunately often coincide in developing countries in South America and Asia. Addressing these challenges requires not just reducing greenhouse gas emissions to slow glacier retreat, but also adapting to changes already underway. This includes improving water use efficiency, developing alternative water sources, building storage infrastructure, changing agricultural practices, and planning for potential water shortages. In a world where fresh water is already a limiting resource in many regions, the loss of glacial water storage is a serious concern, one that connects the remote ice of high mountains to the daily lives of hundreds of millions of people living downstream. Extreme glaciers, records, and remarkable examples. Among the world's glaciers, some stand out for their extreme characteristics. the fastest, the largest, the oldest, the most remote, or the most scientifically significant. These remarkable glaciers offer insights into the diversity of glacial phenomena and remind us that while all glaciers share fundamental properties, they can vary enormously in their behavior and characteristics. Let's start with speed. Jakobshavn Isbre in Greenland holds the record as the fastest-moving glacier reliably measured. This massive outlet glacier drains a significant portion of the Greenland ice sheet, and at its peak, it has been clocked moving more than 40 meters per day during summer months, over 14 kilometers per year. To put this in perspective, you could stand beside it for a few hours and potentially witness measurable movement. This glacier is also one of the most productive in terms of iceberg generation, calving enormous quantities of ice into Ilulissat Ice Fjord, which fills with icebergs of all sizes, some as large as office buildings or larger. The speed of Jakobshavn has fluctuated over time. It accelerated dramatically in the 90s and thousands as it retreated and thinned, losing its floating ice tongue. At its peak around 2012 to 2013, it was moving faster than ever recorded. Interestingly, it slowed somewhat after 2010, partly because of changes in ocean temperatures affecting the amount of warm water reaching its base. This variability highlights how sensitive glacier dynamics are to subtle changes in conditions. At the other extreme, some glaciers move so slowly they're nearly stagnant. Portions of the Antarctic ice sheet in the interior move at sea speeds measured in centimeters per year, taking thousands of years to flow from the central ice dome to the coast. These slow-moving regions preserve the oldest ice on Earth, with ice cores from East Antarctica containing ice up to 800,000 years old, and some estimates suggesting ice up to 1 million years old or more may exist in certain locations. Speaking of size, the Antarctic ice sheet dwarfs all other glaciers. It covers approximately 14 million square kilometers and contains about 26.5 million cubic kilometers of ice. If we think of this as a volume, it's enough ice to cover the contiguous United States to a depth of about 25 kilometers. The ice is over 4 kilometers thick in its deepest parts. The sheer scale is difficult to comprehend. The Lambert Glacier, one of the outlet glaciers draining the East Antarctic ice sheet, is over 400 kilometers long and up to 100 kilometers wide in places, making it the world's largest glacier by some measures. The Greenland ice sheet, while smaller, is still immense at about 1.7 million square kilometers, roughly 3 times the size of Texas. The thickest ice exceeds 3 kilometers in depth. If you stood at the center of the Greenland ice sheet, you'd be on a dome of ice rising over 3,000 meters above sea level, and the nearest rock would be beneath your feet, under 3 kilometers of ice. Among mountain glaciers, the Fedchenko Glacier in Tajikistan is often cited as the longest, stretching over 77 kilometers through the Pamir Mountains. The Siachen Glacier in the disputed Kashmir region between India and Pakistan is 76 kilometers long and notable for being one of the world's highest battlefields. With military outposts established by both countries on the glacier itself at elevations exceeding 6,000 meters. Alaska's Bering Glacier is the longest glacier in North America at about 190 kilometers from its source to its terminus. It's one of the largest temperate surging glaciers in the world. It has surged repeatedly, most recently in 1993 and in 1995, when it advanced several kilometers in just a few months. Some glaciers are remarkable for their accessibility and scientific importance. The South Cascade Glacier in Washington state has been continuously monitored since 1952, providing one of the longest uninterrupted records of glacier mass balance in the Western Hemisphere. This relatively small glacier, covering just over a square kilometer, has lost about 1/3 of its volume since monitoring began, serving as a clear indicator of regional climate trends. The Quelcaya ice cap in Peru, one of the largest tropical ice masses, has been studied intensively because its ice cores provide climate records for the tropical Andes. The Summit Glacier on Mount Kilimanjaro, though not technically a single large glacier, but rather several ice fields and glaciers, has become an iconic symbol of glacier retreat. Since 1912, it has lost over 80% of its ice area, transforming from an ice-covered summit to one with only scattered remnants clinging to the peak. Some glaciers have distinctive and remarkable features. Blood Falls in Antarctica releases red-colored water from beneath Taylor Glacier. The color comes from iron-rich, salty water that has been trapped beneath the glacier for perhaps 1 million years or more, isolated from the atmosphere. When this water occasionally seeps out, the iron oxidizes upon contact with air, creating the striking red color. The subglacial ecosystem in this brine pool is one of Earth's most extreme environments, with organisms surviving in nearly frozen, salty, oxygen-free conditions. Perito Moreno Glacier in Argentine Patagonia is unusual because, unlike most glaciers worldwide, it has remained relatively stable in recent decades, neither advancing dramatically nor retreating. It's famous for periodically damming a side channel of Lago Argentino, creating a temporary lake that eventually bursts through the ice dam in a spectacular rupture that can send house-sized blocks of ice tumbling. This rupture has occurred about every 4 to 5 years on average, though the timing is unpredictable. Vatnajökull in Iceland is Europe's largest ice cap by volume and sits atop some of Iceland's most active volcanoes. The interaction between ice and volcanic heat creates unique phenomena. When volcanoes beneath the ice erupt, they rapidly melt enormous quantities of ice, leading to Jökullaups, catastrophic glacial outburst floods that can reshape landscapes in hours. The 1996 eruption of Grímsvötn volcano beneath Vatnajökull generated a flood that peaked at an estimated 50,000 cubic meters per second, one of the largest flood discharges ever recorded. Some glaciers are scientifically important for other reasons. The Aletsch Glacier in Switzerland, the largest glacier in the Alps, was designated a UNESCO World Heritage Site, partly for its scientific significance. It has been studied for over a century, providing long-term records of alpine glacier behavior. The Columbia Glacier in Alaska was the subject of intensive study during its dramatic retreat beginning in the 1980s, which has provided crucial insights into how tidewater glaciers can rapidly collapse. In Antarctica, glaciers like Pine Island and Thwaites have gained attention because they're losing mass rapidly and could contribute significantly to sea level rise if their retreat continues. Thwaites Glacier, sometimes called the Doomsday Glacier in popular media, is of particular concern because its base lies on bedrock below sea level that slopes downward inland, a configuration that can make retreat self-reinforcing. If Thwaites were to collapse completely, it could raise sea level by over half a meter, and its loss might destabilize other parts of the West Antarctic ice sheet. The fastest retreating glacier measured might be the Hectoria Glacier in Antarctica, which retreated about 8 kilometers in just 2 months in 2022, as mentioned earlier. This rate, if sustained, would see the glacier lose 50 kilometers in a year, though such rapid retreat cannot continue indefinitely. Some glaciers are notable for their sheer inaccessibility. Glaciers in the interior of Antarctica or in remote mountain ranges like the Karakoram have been studied primarily through satellite imagery and occasional expeditions. The difficulty of reaching these glaciers makes direct measurements challenging. Yet, satellite technology has enabled monitoring even the most remote ice masses. Glaciers also exist on other planetary bodies. Mars has polar ice caps composed of water ice and carbon dioxide ice, and glacial features suggest that flowing ice has shaped Martian landscapes in the past. Some of Jupiter's moons, particularly Europa, are thought to have thick ice shells covering subsurface oceans, and the ice may flow and deform like glaciers on Earth, driven by tidal heating rather than solar warmth. These extreme and remarkable glaciers remind us of the diversity within the glacial world. From the miles-thick ice sheets burying entire continents, to small cirque glaciers clinging to mountain peaks. From ice moving at speeds visible to the human eye to ice nearly frozen in place, glaciers demonstrate that ice, given the right conditions, can behave in myriad ways. Each glacier has its own story, shaped by its climate, its geography, and the forces of gravity, temperature, and time. In their extremes, we see the range of possibilities, the limits of what ice can do, and the surprising behaviors that emerge when solid water meets the forces that shape our planet. Life and legacy. As we draw our journey through the world of glaciers toward a close, it's worth reflecting on what glaciers mean beyond their physical presence, beyond their roles in water supply and sea level rise. Glaciers are archives, storytellers, and witnesses to the long arc of Earth's climate history. They connect us to timescales far beyond human lifetimes, to processes that unfold over millennia, and to a planet that has been and continues to be in constant flux. The ice in glaciers is old. In the accumulation zones of glaciers, snow that fell decades or centuries ago is preserved, compacted into ice that slowly flows down glacier. In the great ice sheets of Antarctica and Greenland, ice can be hundreds of thousands of years old. When scientists drill ice cores from these sheets, they extract cylinders of ice that serve as physical samples of ancient atmosphere, ancient dust, ancient volcanic ash, all preserved in chronological layers. The deepest ice cores provide climate records extending back 800,000 years, nearly 1,000,000 years of continuous climate history. In those layers, we can read the rhythm of ice ages and interglacials, the rise and fall of temperatures, the waxing and waning of greenhouse gases, the eruptions of distant volcanoes whose ash settled on ice sheets and was buried. We can see, with extraordinary precision, how Earth's climate has varied naturally, and we can see, with equal clarity, how recent changes driven by human activity depart dramatically from natural patterns. Glaciers also teach us about time itself, or at least about our perception of it. We live in a world of rapid changes, of news cycles and social media, where events from a few years ago feel like ancient history. But glaciers operate on different timescales. The ice in a large glacier may take thousands of years to flow from its accumulation zone to its terminus. The landscapes carved by ice ages 20,000 years ago still shape the world we inhabit. The valleys, lakes, and coastlines we see today are, in many places, products of ice that melted away millennia ago. This perspective can be humbling. It reminds us that human civilization, which feels so permanent and dominant, is a very recent phenomenon on a planet that has undergone vast changes long before we existed. The Great Lakes, which feel like permanent features, are actually young in geological terms, created by ice sheets that vanished only 10,000 to 15,000 years ago. The fjords of Norway, the valleys of Yosemite, the lakes of the Canadian Shield, all are recent creations, carved and shaped by ice in the blink of geological time. Glaciers also connect us to the broader Earth system in ways we don't always appreciate. The ice sheets of Greenland and Antarctica influence ocean circulation by releasing cold, fresh meltwater into the sea. This affects the density of seawater, which drives deep ocean currents that transport heat around the planet. Changes in ice melt can affect these currents, potentially influencing climate patterns far from the ice sheets themselves. Some scientists have raised concerns that rapid melting of the Greenland ice sheet could disrupt the Atlantic meridional overturning circulation, a major current system that includes the Gulf Stream, with potential impacts on climate across Europe and North America. Glaciers also affect the Earth's crust. The immense weight of ice sheets depresses the land beneath them, a process called isostatic depression. In places where ice sheets once existed but have since melted, the land is still rebounding upward, a process that will continue for thousands of years. In Scandinavia, the land is rising several millimeters per year as it recovers from the removal of the ice sheet that covered it during the last glacial period. In some coastal areas, this uplift actually counteracts sea level rise, causing relative sea level to fall even as global sea level rises. The study of glaciers has also driven technological and scientific innovation. Remote sensing technologies, including satellite radar and laser altimetry, have been developed and refined partly to study ice. These technologies now have applications far beyond glaciology, in agriculture, forestry, oceanography, and many other fields. The mathematical models used to simulate glacier flow have contributed to our understanding of fluid dynamics and material behavior under extreme conditions. The techniques developed to drill and analyze ice cores have been adapted to study lake sediments, ocean cores, and even extraterrestrial samples. Glaciers have cultural and spiritual significance for many people. Indigenous peoples living in glaciated regions often have deep cultural connections to the ice. In the Andes, glaciers are sometimes considered sacred, the dwelling places of spirits or deities. In the Himalayas, certain glaciers and mountains are revered as holy. The loss of these glaciers is not just an environmental or economic issue, but a cultural and spiritual one as well, erasing features that have been part of human landscapes and belief systems for centuries. For the broader public, glaciers often serve as tangible symbols of climate change. While atmospheric carbon dioxide concentrations and global average temperature anomalies are abstract numbers, a photograph comparing a glacier in 1950 and the same glacier in 2020 tells an immediate, visceral story. Glaciers make climate change visible in a way that few other phenomena do. Their retreat serves as a warning, a call to attention, and increasingly, a motivation for action. Looking forward, the fate of glaciers is inextricably linked to human choices about greenhouse gas emissions. If emissions are reduced rapidly and substantially, many glaciers will continue to retreat for decades due to warming already in the climate system. But the rate of loss can be slowed, and some glaciers can stabilize. If emissions continue at high levels, the losses will be much more severe, with many smaller glaciers disappearing entirely, and even large ice sheets experiencing substantial retreat. The consequences of these outcomes differ dramatically. Under high-emission scenarios, sea level rise could exceed 1 meter by 2100 and continue rising for centuries thereafter, potentially reaching several meters. Millions of people would be displaced. Countless ecosystems would be transformed. Water supplies for hundreds of millions would be disrupted. Conversely, limiting warming to 1.5 or 2 degrees Celsius above pre-industrial levels, while still allowing significant glacier loss, would spare much of this damage. Glaciers, in a sense, are asking us a question. What kind of world do we want to create for the future? How much are we willing to change to preserve the ice, the water supplies it provides, the ecosystems it sustains, and the climatic stability it represents? These are not questions glaciers can answer. They simply respond to the conditions we create, advancing when we make the world colder, retreating when we make it warmer. They're indicators, messengers, and in their silence, perhaps the clearest communicators we have about the state of our planet's climate. Closing reflection. And so our journey through the world of ice draws gently to a close. We've traveled from the first snowflakes falling in high, cold places to the vast ice sheets covering continents. We've explored how ice forms and flows, how it carves landscapes and stores water, how it responds to climate and shapes the future. We've seen glaciers in their diversity, from the smallest cirque glaciers to the miles-thick ice sheets, from frozen rivers moving at a crawl to surging torrents of ice racing down valley. You've learned that glaciers are not static monuments, but dynamic systems, sensitive to temperature and snowfall, advancing and retreating in response to climate, sometimes moving perceptibly over days, other times flowing imperceptibly over millennia. They are sculptors that carved many of the world's most dramatic landscapes, archives that preserve climate records extending back hundreds of thousands of years, and reservoirs that store fresh water for hundreds of millions of people. You've heard how ice ages have come and gone, driven by subtle changes in Earth's orbit, amplified by feedbacks involving ice, greenhouse gases, and ocean circulation. You've learned that we're currently in an interglacial period within an ongoing ice age, and that without human influence, Earth would eventually, over thousands of years, slide into another glacial period. But human activities have altered the climate system so profoundly that we've likely prevented the next glaciation and instead embarked on a period of rapid warming unprecedented in recent geological history. You have seen how glaciers worldwide are retreating, losing mass at accelerating rates, contributing to rising seas, and changing the water supplies upon which hundreds of millions depend. You've learned that these changes are driven primarily by increasing greenhouse gas concentrations in the atmosphere, the result of burning fossil fuels and altering land use. And you've heard that the future of glaciers depends on choices humanity makes in the coming years and decades about emissions, energy use, and our relationship with the planet. But beyond the facts and figures, beyond the mechanisms and consequences, perhaps what matters most is the connection. Glaciers connect us to time, to climate, to water, to landscapes, and ultimately to the realization that we are part of a planetary system, not separate from it. What happens to glaciers affects us. What we do affects glaciers. We are connected, and in recognizing that connection, we might find both humility and motivation. As you drift towards sleep tonight, perhaps you can imagine standing at the edge of a glacier, feeling the cold air flowing down from the ice, hearing the trickle of meltwater, seeing the blue depths of a crevasse, and knowing that beneath your feet lies ice that fell as snow when your grandparents were young, or even long before humans built cities or wrote history. There's something profound in that. Something that transcends the daily concerns and reminds us that we're part of something much larger and much older than ourselves. The glaciers are speaking to us if we're willing to listen. They're telling us about the past, warning us about the present, and showing us with cold clarity what futures are possible. They're asking us to pay attention, to care, to act. And in their slow retreat, they're reminding us that change, once set in motion, can be difficult to stop, but that the choices we make today will echo into the distant future, shaping the world not just for our children, but for their children's children, and beyond. I hope this journey into the world of glaciers has given you something to think about, something to wonder at, and perhaps a deeper appreciation for the frozen water that shapes our planet. If this exploration helped you unwind or gave you a peaceful way to end your day, I'd be grateful if you'd take a moment to like this video and subscribe to the channel. It helps others discover these calm conversations about science, and it lets me know that these explorations matter to you. Sleep well, dream softly, and remember that even as you rest, glaciers are flowing, ice is forming, and the great cycles of Earth continue their patient, endless turning. Good night.